the pilot shoved his control stick forward. The Spitfire's nose dropped. For a split second he felt weightless, hanging in his straps as the aircraft tipped into a steep dive over the gray strip of the English Channel. In every other dive like this, he knew exactly what would happen next. The Merlin engine would cough. Then sputter. Then die. And somewhere behind him, a German Bf-109 would still have full power, dropping in like a hawk on a bird with broken wings. But this time, the engine kept roaring. He held the dive. Closed the distance. Opened fire. What changed? Not a brand new engine. Not some huge redesign from the factory. A tiny brass washer, smaller than a coin. Designed by a woman almost no one at the airfield had even heard of. Welcome to War Era Records. Today we're telling the story of Beatrice Tilly Shilling, the engineer whose little brass invention quietly saved hundreds of Allied pilots, and helped close one of the Luftwaffe's biggest advantages in the air. If you enjoy stories where the hero wears oily overalls instead of a uniform, make sure you subscribe to War Era Records and turn on notifications. We bring forgotten war stories back to life, one episode at a time. Now, let's go back to the start of Tilly's War. A problem killing more pilots than bullets. In 1940 and early 1941, RAF fighter pilots were flying some of the finest aircraft in the world, Spitfires and Hurricanes, powered by the legendary Rolls-Royce Merlin. On paper, they were fast, agile and every bit a match for the German Messerschmitt Bf-109. In reality, there was a deadly catch. Every time a British pilot pushed the nose down hard into a -G dive to chase a German fighter, the same thing kept happening. The Merlin's carburettor would flood. Fuel sloshed away from where it was supposed to be. For about a second and a half, the engine lost power. 1.5 seconds does not sound like much. In a dogfight, that is an eternity. In that tiny window, a Bf-109 could pull away to safety. Or worse, loop back, line up the now gliding Hurricane or Spitfire, and shred it with cannon fire while the British pilot frantically tried to restart his engine. German fighters didn't suffer this problem. Their Daimler-Benz engines used direct fuel injection, which didn't care whether the aircraft was upright, inverted, pulling +G or -G, fuel kept flowing. Power stayed on. German pilots knew the British weakness. They used it. British pilots knew it too. They feared it. The RAF could not afford to lose experienced pilots to a fuel system quirk. That nightmare landed squarely on the desk of one engineer at the Royal Aircraft Establishment, Farnborough. Her name was Beatrice Shilling. Meet Tilly, the engineer who refused to slow down. Picture the engine department at Farnborough in 1939. Mostly men in white coats and oil-stained coveralls, arguing over fuel mixtures and compression ratios. And in the middle of them, a small, tough woman with sharp eyes and zero patience for nonsense. That was Tilly. By the time the war started, she had already taught herself engines as a teenager by buying a motorcycle, stripping it down, and rebuilding it. Raced that motorcycle at Brooklands at over 100 miles per hour. Earned the coveted gold star for lapping the circuit fast enough, something only a handful of riders, and even fewer women, had ever done. She wasn't a mascot. She wasn't helping out. She was the principal technical officer responsible for carburettor research. Most of the men around her had never worked with a female engineer before. Some of them didn't think women belonged in engineering at all. Tilly had no interest in their opinions. Her focus was entirely on one thing: keeping pilots alive. The carburettor trap. Here's the problem in simple terms. The Merlin engines in Spitfires and Hurricanes used float-type carburetors. Inside, there was a small chamber with fuel and a float that kept the fuel level steady under normal conditions. In level flight and gentle turns, this worked fine. But when a pilot shoved the nose down hard, creating -G, the fuel inside the chamber did the same thing your drink does when a car slams on the brakes. It surged in the wrong direction. Fuel flowed where it shouldn't. Air and fuel mixture went wrong. The engine starved for fuel at the jet, then flooded. Result: the engine cut. The aircraft hesitated or lost power entirely. Meanwhile, the German Daimler-Benz 601, with fuel injection, didn't care what the G-load was. It simply kept feeding fuel under pressure. This meant A German pilot could bunt forward into a dive to escape. The British pilot who tried to follow would lose power. The chase would end right there, usually with the British fighter in trouble. New pressure carburetors were on the drawing board, a more sophisticated fix, but they wouldn't be ready for years. The war was not going to wait. A tiny part with a huge job. Tilly looked at the problem like this. If the carburetor flooded under -G because fuel was allowed to surge freely, what if you simply limited how quickly the fuel could move? Not shut it off. Not starve the engine. Just put a strict speed limit on the fuel flow. Her idea was incredibly simple. Place a small brass restrictor in the fuel line leading to the carburetor. Give it a hole just big enough for maximum required fuel at full power. Small enough that sudden -G forces could not dump extra fuel into the carburetor and drown it. The challenge was in the details. If the hole was too wide, the carburetor would still flood. If it was too narrow, the Merlin would not get enough fuel at full power and could fail in some other, equally deadly way. Tilly spent months running tests, machining piece after piece, checking flow rates, measuring pressure, chasing that perfect balance. Eventually she arrived at a design, a simple brass washer with a precisely calculated aperture. Easy to make. Easy to install. Barely visible once fitted. It worked on test rigs. Bench engines ran through simulated -G maneuvers without cutting out. But bench engines don't get shot at. They don't dive at hundreds of miles an hour while someone is trying to kill you. To prove the idea, Tilly needed a live test. On a real aircraft. In real combat. We'll find out in the air. This is where the story becomes less like a lab report and more like something out of a thriller. The official route would have taken months, paperwork, committees, cautious trials, approvals from the Air Ministry. Pilots were dying now. So Tilly did something that could have ended her career. She went to an operational fighter station with a handful of her brass restrictors in her bag and found someone she trusted, a senior ground crew sergeant who had seen too many aircraft crash for no good reason. She explained her idea. He understood the risk. He said yes anyway. They selected a Hurricane due to fly a patrol that morning. The pilot was already strapped in. The engine was warming up. In a tiny window of time before takeoff, the sergeant briefly opened the fuel line, slid Tilly's restrictor into place, secured it, and checked the connection. To anyone glancing at the aircraft, nothing looked different. The pilot had no idea he was about to test a completely unapproved modification in live combat. The Hurricane took off, climbed, and headed toward the coast. Tilly stayed on the ground, staring at the sky, running fuel flow calculations in her head and thinking about all the ways this could go wrong. If the restrictor didn't work, the worst-case scenario was brutal. The engine might quit completely at full throttle. The pilot could die in the air. And she would have to live with knowing that a change she made had killed him. Time dragged. No radio drama. No emergency call. Then, finally, 3 fighters reappeared in the distance, circling back toward the field. All 3 landed. The Hurricane that carried her restrictor rolled in. The pilot climbed down, helmet under his arm. He was not shaken. He was excited. He reported that he had dived hard on German fighters, felt the -G that usually killed his engine, and this time, nothing bad happened. The Merlin sang all the way down. He finished his attack. He came home. Only then did Tilly tell him what they had done to his fuel line. His response was simple. Whatever that thing is, put it on every aircraft here. War on regulations. There was one small problem. None of this was authorized. From the point of view of regulations, Tilly had just modified a combat aircraft. Without permission. Using an unapproved part. Then sent it into a live engagement. If it had gone wrong, it could have meant courts, blame, and scandal. But the thing about wartime is this: when something clearly saves lives, rules suddenly become very flexible. Pilots who had experienced engine cuts in dives did not need a long explanation of fluid dynamics. A single successful mission sold them instantly. Word started to spread from squadron to squadron. At first, only a few aircraft at that base quietly received the new restrictor. The results were the same: -G dives with no loss of power, repeatable and reliable. Calls started coming in from other stations. "We heard you've got a fix. Bring it here." The Air Ministry, once fully informed, did not shut the project down. Instead, it did what war ministries do when they smell an edge: it accelerated everything. Production contracts followed. Factories began machining the little brass parts by the hundreds, then thousands. Tilly formed a small traveling team, loaded up motorcycles and vehicles with tools and boxes of restrictors, and went from airfield to airfield, overseeing installation. Each one took minutes to fit. No need to pull engines out. No need to ground squadrons for days. Soon, Hurricanes and Spitfires all over Britain were flying with Tilly's tiny brass Guardian in their fuel lines. Miss Shilling's orifice. Fighter pilots deal with stress in some interesting ways. They gave the restrictor a nickname that would make a schoolteacher raise an eyebrow. Miss Shilling's orifice. Crude, cheeky, very RAF. Tilly didn't complain. She knew exactly how men under constant fear coped. If a slightly dirty joke made them remember to ask for the part, she was fine with it. Behind the humor was something serious: trust. Pilots who had once been terrified of pushing into a hard dive now had confidence that their engines would stay with them. Statistically, the impact was huge. Engine failures during diving attacks, once a common and deadly occurrence, became rare. RAF fighters could now use tactics that had previously been too risky. German pilots lost a key advantage they had enjoyed since the start of the air war. The little washer didn't win the war on its own, of course. But it took away a major German edge and kept experienced British and Allied pilots alive long enough to fight, teach newcomers, and lead squadrons later in the war. For a part that cost almost nothing and could sit on your thumbnail, that is an extraordinary achievement. Beyond the washer. You might think that after creating one of the most famous small parts in aviation history, Tilly would have stepped into a desk job and lived on her reputation. She did the opposite. Through the rest of the war, she tackled a long list of other life-or-death engine problems. How to start aircraft reliably in Arctic conditions, where oil turned to sludge and batteries froze solid. How to keep engines running smoothly at very high altitudes, where air is thin and fuel mixtures become extremely sensitive. How to improve superchargers and fuel systems for later versions of the Merlin and other engines. While her husband flew dangerous missions in bombers over Germany, she stayed in the laboratories and test bays, trying to make sure that when aircrews reached enemy territory, their engines didn't fail them. After the war, she kept working at Farnborough through the jet age, studying things like wet runway braking and even helping design a bobsleigh for RAF competitions, applying aerodynamics and engineering to a very different kind of speed. Through it all, she kept riding and maintaining her beloved motorcycle, the same Norton that had carried her around Brooklands before the war. Recognition and legacy. In 1948, Beatrice Tilly Shilling was awarded the Order of the British Empire for her wartime work. She never became a top administrator. Those positions were still mostly closed to women at the time. But the respect she earned among pilots and engineers was real and lasting. When she finally retired in 1969, she left behind dozens of technical reports and improvements, safer aircraft and better understood engines, and one tiny brass washer that had quietly changed the air war over Europe. Today, buildings, pubs, and memorials bear her name. Museums display examples of her restrictor in glass cases. Visitors walk past, see a small brass ring with a hole in the middle, and read that this almost invisible component once helped swing the balance in deadly dogfights high above the channel. It is a perfect lesson in wartime engineering. You don't always need something big, flashy, or complicated. Sometimes, victory hangs on the work of a stubborn engineer, a piece of scrap metal, and a very small, very smart idea. You've been watching War Era Records. If Tilly Shilling's story surprised you, do 2 quick things for us. Hit the like button so this video gets pushed out to more people who have never heard her name. Subscribe and turn on the bell so you don't miss our next story from the hidden corners of World War history. And now it's your turn. Tell us in the comments where you're watching from. Did someone in your family serve in the war, in the air, on land, or at sea? Have you ever heard of Miss Shilling's invention before today? Your comments and your memories help keep these stories alive. This is War Era Records, signing off for now. We'll be back with another story of real people, real decisions, and the small details that changed the course of the war.